Okay, so this is a presentation about Amazon MemoryDB, a fast and durable memory-first cloud database, which was written by 6 AWS engineers for Sigmod this year. And the problem that they're trying to solve is with Redis. So Redis is popular because it's fast and it supports fairly complex data structures. So it can do things like there's a list structure, and one atomic operation can pop something from the list and return it to the client. Uh, it's it's often called like a data structure server, and that makes certain kinds of applications really easy to write and really easy to coordinate. But it has very poor durability, and it doesn't support consistent follower reads. So the poor durability story is it just does simple async replication from the leader to the followers. So the leader executes each transaction and acknowledges it before writing the operation to its transaction log and before confirming that a majority has replicated it. So if the leader crashes, the new leader may or may not have any of those operations. There's usually some sort of write loss with a leader crash. It also doesn't support consistent follower reads, although now that I'm reading this slide that I wrote, MemoryDB doesn't solve this problem. So I would say that that is not part of the solution. So let's focus on durability. And the problem that AWS wants to solve is that they want to sell a better Redis to their customers. Now, when I say Redis, that name is in dispute. There's been some license drama. The Redis Labs, which maintains Redis, changed their license from open source to source available, which I certainly understand why they did that. But some community members forked off the open source version so they could keep developing it in the open, and that's called Valkey, and it's got a new logo, although since Valkey sounds like a Norse hero to me, I think this should be their logo. Regardless, AWS marketing still says that MemoryDB is OSS Redis compatible. They don't mention Valkey, so I don't know what the long-term outcome of this all will be. So I'm just going to say Redis in this presentation. Amazon wants to sell a better Redis with stronger durability. How are they going to do it? Their solution is they're just going to keep using Redis. They want full compatibility. They're not going to re-implement it. They're going to add durability and consistency, although as we go through this presentation, I keep thinking that maybe they're not improving consistency after all. I guess they're improving leader consistency, but not secondary consistency. So we're improving durability and consistency, but of course we know with a distributed database that doing this involves a lot of complexity. So what the authors do to deal with this is they make a black box, they call it the transaction log, they stick all of the complexity in the black box, and they close the black box. The paper does not describe the transaction log internals. We don't know how it provides the guarantees that MemoryDB relies on. I hope and presume that that will be in some future paper. For now, I'm just assuming that the transaction log is wrapped or Paxos under the hood. Basically, the only thing they tell us about it is that it does multi-availability zone replication, and it has some linearizability type guarantees that MemoryDB can rely on. So this is a little frustrating for us because we're the distributed systems reading group, and this isn't really, I would say, a distributed systems paper. I think it's mostly a software engineering paper. It's about how Amazon decomposed Redis into the transaction log and everything else and then they replaced the transaction log with a better one, and then they stuck it all back together and called it MemoryDB. The MemoryDB architecture, clients somehow know who the primary is, they send it writes and most of their reads. There's the multi-availability zone transaction log, which is what they've used to replace Redis's own replication layer. It's got little locks icons on it. Maybe that's to indicate that it's proprietary and we're not allowed to know how it works or something like that. And then whenever the primary writes a entry to the transaction log, those are eventually replicated to all of the followers, and there can be 0 or more followers. The cool thing about this is that since the replication factor is now part of the log, you can have a single primary and still be guaranteed durability, even if the primary fails. Now, in Redis, replication is async. The primary acknowledges a write as soon as it executes it without waiting for replication. And MemoryDB, on the other hand, always waits for the log to make a write durable before the primary acknowledges it to the client. So how do we accomplish that without rewriting the core of Redis? MemoryDB has a thingy called a tracker. The tracker knows when writes become durable, and it delays acts until then. And it also blocks reads on dirty data to prevent clients from seeing something that could be lost. So together, all of this guarantees linearizability to the client. My impression is that the tracker is living outside of the Redis core, and it's intercepting writes and reads and acknowledgements and transaction log acts, and putting that all together to create this linearizable view of a system that is fundamentally not linearizable. Writes are replicated to secondaries only after they are multi-AZ durable. And so replicas will never execute dirty reads because they don't have the data yet. A client can opt into reading from one replica. It will get sequential consistency. And I guess that is stronger than Redis's open source consistency, because you won't see a write that will later disappear for you. And then if you opt into reading from multiple replicas, then you'll get eventual consistency. The advantages they get from disaggregating the log. So we've seen other disaggregated log architectures. I think that Aurora is the most influential of these, but there's also Socrates and Delos, and we've read a few other papers where the log becomes a separate first-class component. The advantages of that in this case are they maintain Redis compatibility because they haven't replaced most of Redis. The log service, because it's multi-availability zone, they're claiming 11 nines of durability, which is a lot of nines. And they can scale the durability separate from availability. So availability means more Redis nodes, and each of those needs a lot of RAM because that's the main resource. It's basically an in-memory database. Even a single leader only deployment, it's low availability because if the leader dies, then Amazon has to restore a new leader from the snapshot, which presumably takes longer than you want. But it is high durability, even though you only have a single leader, since the transaction log is internally replicated among multiple availability zones. You have those 11 nines of durability guaranteed. The leader only writes to the log, so that's one message. And then the log is doing the fan out. to the followers, the kind of write amplification, so that offloads some work from the leader. I think any offloading from the leader is good because Redis is not very scalable, it's single-threaded. And also the log is used in leader election, which ensures one leader and that the leader has all of the committed rights. So these are the same sorts of guarantees you would get with Raft with leader leases, but Redis itself does not guarantee either of these things. And the final advantage is that they have what they call off-box snapshotting. So Redis's own snapshot, first of all, why do you want a snapshot? Snapshots are useful for disaster recovery. If a user deletes all the data, you can restore from an old snapshot. And also it's a quick way to create a new follower is that you restore it from an old snapshot and then you catch it up by replaying new log entries. Redis creates snapshots by forking the process. One child keeps serving transactions, so it's modifying the data and it uses the Linux or the Unix copy on write optimization, and then the other child executes the snapshot, so it writes it to somewhere. This means that the two children are competing for CPU, and then if it's a write-heavy workload, they're also competing for RAM. Redis users tend to massively over-provision the RAM on their boxes just to make room for occasional snapshots. So with the log disaggregated, we get away from this need to over-provision the box. With MemoryDB, when Amazon wants to take a snapshot, they start up a separate machine running Redis. They restore it from the most recent snapshot. They catch it up by writing all of the transaction log entries up to some recent point. And then they save a new snapshot to S3 and kill the box. And this means that the machines serving the customer only need enough capacity to do their regular workload. There are 3 dimensions for scaling Redis nodes. You can change the number of replicas. There's also vertical scaling, so you can use more or less powerful instances for each of the Redis nodes. And then you can also add or remove shards. Redis supports sharding, which I haven't talked about so far. We will talk about it in a second, but you can add or remove shards for horizontal scaling. And presumably the log service can also scale, but that's a secret from us, so we don't know. To add a replica, you do the obvious thing, you restore one from the most recent snapshot and then replay the transaction log. And adding replicas is useful for either scaling out inconsistent reads by doing secondary reads, or to improve availability. So you can lose any number of Redis nodes with a fairly short downtime, so long as you still have a hot standby available. For vertical scaling, which we'll see in a second is not actually very useful because Redis doesn't scale well, but for vertical scaling, you can replace each follower with a bigger instance and then hand over leadership and then delete the old leader, or replace it with a smaller instance and do the same thing. The paper says that MemoryDB has a collaborative leadership transfer where the old instance actively hands over leadership, which minimizes downtime. And that's it. They don't say anything more about the handover algorithm. MongoDB and other systems have similar ideas, so we could guess that it works like the old leader ensures that the successor is reasonably caught up, and then the old leader stops accepting rights, it streams the final changes to the new leader. The old leader relinquishes its lease and tells the new leader to run for election instantly, so they don't have to wait for any timeouts. And then the whole handover should have a write unavailability period that's very, very short. And then to change the number of shards, so Redis supports consistent hashing with 16,000 slots. Each slot has a subset of all of the keys, and keys are assigned to slots according to their hash. And then each shard of a replica set owns some subset of the slots which are signed. And then there's some kind of catalog that contains the mapping of slots to shards. And I don't know how Redis, open source Redis, changes the number of shards or reassigns slots. The paper doesn't cover that. In MemoryDB, slots are reassigned in the way that you'd expect, where the old leader streams data and changes, or the old owner streams data and changes to the new owner, and then blocks writes, streams the final changes. They both commit a change to the metadata to transfer ownership. And then after that, any kind of lingering requests to the old owner are rejected and redirected to the new owner. They've got a clever section about upgrading. So for any version 1 and version 2, I mean, upgrading the software version of Redis or of MemoryDB. So for any version 1 and version 2, the new version 2 can read version 1's log entries, but maybe not vice versa. So we're concerned that if an old Redis sees a new Redis's log entry, it could crash or do the wrong thing. So to avoid this, all log entries are marked with the leader version that created them. And they upgrade followers to version 2 first, and then finally the leader. So generally speaking, you shouldn't see a log entry created by a newer version than you are, but there could be a failover in the middle of the upgrade process. So if a V2 node does become a leader, V1 will stop replicating. It won't replicate any entries created with a newer version than itself. Meanwhile, as long as there's a mixed version in the cluster, snapshots are built with the V1 engine until all nodes are V2 to ensure that if they need to do an emergency downgrade, they'll be able to roll back to V1. So I thought all of this was kind of a useful best practice. MongoDB, we do something much more complicated and different. So I thought this was all kind of elegant and something that other people might emulate. In their evaluation is pretty short, which I don't mind. I thought this was the most interesting chart. On the left is a read-only workload. And on Amazon large and extra large instances, Redis and MemoryDB have about the same throughput for reads. And then when the size is upgraded to 2XL, there's a step change. MemoryDB gets remarkably faster, and then there's no further benefit to it. The paper just has one sentence. They say this is because of enhanced I/O multiplexing, which means that with MemoryDB, some of the I/O work can be offloaded from the main Redis thread to background threads. So they can take some additional advantage of multiple CPUs compared to open source Redis. And apparently that removes a bottleneck when they upgrade to 2XL, but then there's another bottleneck that they hit and that's not relieved. Further upgrades are not useful. So it seems like the only useful thing you can do with MemoryDB is upgrade from XL to 2XL, at least for very read-heavy workloads. For write-heavy workloads, Redis writes faster than MemoryDB, as we would expect, because it isn't waiting for replication. I don't know if we would expect that since everything's pipelined. Maybe this is the memory, maybe this is the enhanced I/O multiplexing also. MemoryDB is much slower, but on the other hand, Redis has no durability guarantee. It's interesting here that upgrading the instance type seems to provide a little bit more scaling than for read-only workloads. This surprises me since all instance types have the same CPU speed generally, just more CPUs, which is not something that I think Redis can use. Maybe this is also because they have more memory. More likely it's because bigger instances have more network throughput, although this chart doesn't match the way that network throughput grows with instance size. So I'm not sure exactly what's going on here, and it would have been nice to have a little bit more analysis of why the chart looks like this. My evaluation is that it's a good industry paper. It's really nicely written. As you can see, there are a lot of details missing, but they do explain things well, and brevity is not a sin. It's frustrating for distributed systems people. I wish that they had published a paper about the log first, or else included some additional log details in this paper. The consistency during upgrade section was the one that really presented new ideas to me that I couldn't have guessed. And so I really liked that little section. And Murat, of course, has already written a summary of this. And then Mark Brooker at Amazon also has a nice little summary of the paper too. I think Mark doesn't add very much compared to just reading the paper, whereas Murat mentions a lot of antecedents and has a nice analysis here. Thank you very much.